All right, good morning to this last week of instruction. We are there, a whole week of review. These are the review sessions. Next week is R week. I'll post, I won't be able to do any other review sessions because all grad students at this entire university want me to be in their qualification exam. But I'll try to squeeze in my office hours as usual. And also, you guys seem to communicate through Piazza a lot anyway, so hopefully that will be working out well. This week, you can think about what you want to do. Today, I was planning we could talk about the programming assignment if there are last-minute questions. A little bit unfair to you guys who had 8 o'clock session, discussion section, but just a few words about it. Then I was thinking of doing, same as the midterm, I go through the material since after the midterm, just showing some problems that I thought were interesting. For Thursday, please comment on what you want to talk about. I did post old exams. So basically, if you look at this announcement I made, the final is what you expected. It's everything, okay? Everything we've done will be on the final. I posted a bunch of old ones. There are not solutions to all of these. Some have solutions, some do not. There are a lot more on this exam archive, and I was thinking one thing I can do. I won't have time to write solutions, but I'm going to go through them and just say which problems are good for you or are covered. So I'll post that in a little bit, so you'll have a lot of practice. And when people ask what is the best thing we can do, obviously going through the old homeworks, programming assignment, etc., and just the slides and reading the book, all those are great preparation. But apart from that, doing old exams is, of course, a great idea. Because if you look at all these, you see they're not that different. We kind of write the same type of problems, and we've done so for decades. So that's a good thing to do, I think. So they don't have solutions either, most of these. If you want to, for those of you who start before Thursday, bring them here on Thursday, and we can solve them together or talk about them. Otherwise, bring them to office hours and try to figure them out. Many of these problems are such that it's a great practice for you guys to actually convince yourself that I'm not justifying that there are no solutions, but having solutions is sometimes not as educational because you just quickly check and you see, oh, you made a mistake. You don't train yourself in finding the mistake. So in a way, the good thing about it is that you can actually practice the real skill of figuring out whether something is correct, especially with a computer next to you for these numerical things, and you can often convince yourself that you got the right result. So a lot of practice material for that. What else did I post? Yeah, just what I want to say about, again, many people have handed it in. The Newton convergence, everybody asked on Piazza. I think you all read it, but I suppose some people missed it, that Newton convergence was all these numbers, f print f, that you want to print out in programming assignment 4. So, hopefully you got that. The only reason is we want to see, Newton convergence will come back. I'm not going to review chapter 2 today, I was thinking, but Newton, it converges quadratically eventually. And we saw that by the doubling of accuracy. And you can get it right. You can get the solution out without having that. It's just that it's going to take too many iterations. So therefore, I ask you to just print it so the GSIs can basically look at it and say, that kind of weeds out all the little tiny errors you can make in Newton. If you get that quadratic convergence, derivatives are right, the formulas are right, almost everything must be right. So that's a good printout to do. And then Dave will come here 15 minutes early and interrupt us, and we'll hand out all these course evaluations for today. That's the plan. All right, any questions? It's review now. You can ask administrative questions about the final or anything. Yeah. Yes. Just going through stuff. No questions. Good. So here's what I'm going to do. I was thinking that, first of all, I thought we should review everything. But I did review, before the midterm, everything up to what we did then, right, including chapter 4. And the only new chapter is this one. But I thought the differential equations is really a big chunk. And if I don't start, especially since we'll have a short lecture today, we'll start with the differential equations. And then we'll try to go into the chapter 6, maybe at the end of today or on Thursday. And if you want to review something specific from before then, we should do that as well. But I emphasize what I said last time. It's cumulative. So everything for the midterm will be covered on the final. And you will get this message loud and clear from the old exams, where everything is mixed. Maybe slightly, the differential equations and the linear algebra will be important, but it's really fairly mixed. So let me just bring up these old slides from chapter 5 and go through and comment on what could be. So the slides are, as you know, I just wrote them. I don't want to do a completely different thing from the book, because that's just confusing for you guys. So I follow the book closely. However, what I put in the slides is, of course, a good indication of what's important to you guys. You can look at the old finals I posted. You can look at the midterm you had, and you realize that most things that I asked for are really, and I'm not going to ask for some weird little comment in the book that I didn't talk about or is not on the slides, right? So I think it's a good idea in that sense to see what's important. Having said that, I really just follow the book. So you can do both. You can use these together. Remember 5.1, we started with some theory. I told you this was 123 stuff, but most of you have not taken 123 and are not planning to. But it's actually fairly brief. It's just an idea of saying whether a differential equation has a solution or not. So the Lipschitz condition could be a new thing for you guys, probably, where we actually define a Lipschitz continuity. And maybe I know many of you are confused about the fact that our f, our right-hand side in the differential equation, has two variables, right? T and y. And the t is not an issue. In fact, what we do usually when we analyze these in the upper level, in the advanced, in the graduate level courses, we remove the t, because it can be absorbed by just rewriting as a system. So what we're really talking about here is Lipschitz in a certain variable, and we're focusing on this y, means that the jump in f can be bounded by some Lipschitz constant times the jump in the independent variable. That's fairly straightforward. And we thought about this back and forth in various ways, exactly how it came between continuity and differentiability. Of course, differentiability means that things are so smooth that you can't really jump too much in function value for a small jump in a dependent variable. While continuity was not quite enough, because you could, in fact, for example, the square root function has this sort of infinite derivative as 0. And that actually means that this Lipschitz continuity does not work out. So it's right in between. There are examples of both. In general, most of our textbook problems are, of course, just simple expressions, right? Sine of t plus y and stuff like that. Usually, we have differentiability, which means that we use this theorem, saying that look for the derivative. Usually, when you're asked for Lipschitz constant, unless there are absolute values and stuff, and we're trying to trick you, this will usually lead it to. You're maximizing a derivative over an interval, that would be a Lipschitz constant. But of course, it assumes that it's differentiable. All right, so why do we do this? Because Lipschitz continuity is exactly the right condition to put on this f in order to ensure things that we want. Okay? I mean, if you have more, that's great, if it's differentiable and all these things. But if you say that this f here is Lipschitz over the interval that you're interested in, you will have unique solution. Okay? So that's what we're looking for. Unique means that the solution exists, and there's only one. And I hope you can appreciate that's good for so many reasons. You have a problem, right? You want to solve it, but especially in numerical analysis, how could we have a theorem saying you converge to the true solution if there 1 is no solution or 2 is more than 1? That would be quite difficult. So we want uniqueness. We talked about well-posedness. We didn't go through this too many details. Just the idea of sensitivity, that every time you solve something numerically, you will add noise delta to your f. You would probably add some noise delta to your, let's see, initial value, right? And what does that noise delta cause to change in your equation? And that's described by the idea of well-posedness, that change should only grow linearly with the size of the perturbation, so a constant times that epsilon. And you know, it's not. That constant could be 1 million, so it could be a huge change. Your pendulum, for example, it's sensitive. It's very, very sensitive. It perturbed by epsilon. I think I asked you to perturb it by 10 to the minus 3, right? And then after a while, it just blew away after a long time, right? So this k could be huge. But if you divide epsilon by 2, it should asymptotically go down by a factor of 2. That's the idea. And then well-posedness comes also from Lipschitz. Same thing. Let's go straight to 5.2 and Euler's method, and then I have a little silly example on that. So we always, almost this entire chapter, we're solving this equation. I would say almost the only exception is when we try to trick you, we put things in front, you have to divide down. The biggest thing is, of course, what you did in the pendulum, where you got a second order initial value problem, right? And that trick is standard. And it's, of course, in chapter 5.9, a lot of it. Namely, you just turn it into a system. But we always try to write, for the methods we talk about, Runge-Kuttas and Multistep, we always write it in this form. We just refer to the f here as the right-hand side often, and this is what we do. You run from a starting t to an ending t. Often this a is 0, and you have an initial value. And we, except for the chapters on variable step size, which we will come to, we often assume equal step sizes. And that can be written in math notation as saying you introduce a bunch of equally spaced times, right? And you just keep on stepping. So all this is the setting for most of these methods. But for now, it's just Euler. Euler's method can be derived in so many ways. We talked about it back and forth. Of course, just going straight at Taylor is the right thing to do. Why? Because it does not only tell us, remember, Euler is really the left part here saying that the new value is equal to the old plus a step size times the slope. That's exactly if it's a straight line, but it's not a straight line, so therefore it's something else. So this is the perfect way to do it because it says if you just keep the straight line part, the part here, h squared half times h second derivative of that's supposed to be a y, sorry, is the error you're doing. Okay, and we will later define that divided by h to be the local truncation error. So anyway, this is Euler's method. It can be written in a short way. We often like to write methods like this. Don't forget the initial condition, but it's fairly obvious. And then you just keep on iterating, and that's the method. Okay? And what do we have? This was a big, important theorem for Euler. We can actually have a proof for error bound. Just like in the quadratures in Chapter 4, we have a proof, a bound. It's not practical, but it's still there. It does, of course, say that you need a Lipschitz condition. In fact, I'm going to need the number coming out of this, because that's going to affect the bound. Unfortunately, this makes it really impractical. There are many reasons this is impractical, but it's theoretically a proof of convergence. This is probably the most impractical part of it, namely that you need to bound the second derivative. You're solving for a solution that you don't know, and now you need to find the second derivative, right? You can actually do that. We don't do it in this course, but you can find that using, in physics, you have energy argument. You can find bounds in other ways, but it's kind of an issue. Then, at least, at the end, you get this bound. It's important to understand what's going on here. Y of t, y is a function, and it's the true solution. Y of ti is the true solution at time t. Wi is your numerical approximation with some method, in this case, Euler's method, right? So the left-hand side is the error at time ti, okay? Often you would probably be asked to say, what is the maximum error? Then you would probably maximize this over all the time steps. Maybe we just want to look, in fact, in your programming assignment, the pendulum one, number 3, we looked at the error only at the last step. So you can do various things. But this is really telling you the error at time ti. And here is the expression. And the m shows up. The worse the m is, the worse it gets. L is in the denominator, but that's well compensated for in being in the exponential here. So high L, meaning that f varies very quickly for small changes, is really, really bad. And another thing that is really, really bad is long integration time. So imagine running this on your pendulum, finding an m, finding an L, and running as long as you did for 100 seconds or something. I'm sure the error bound would be completely insane. It wouldn't tell you anything about the solution. But at least, if you look at this, it does really write this error as h times something that has no h in it. Remember when we proved this, there were h's and n's, big n's, right, all over the place. That's hard to see. That's not a proof of convergence, really, because we don't see what's going on. We worked hard to eliminate all that and write all this. I mean, L and M are properties of the problem. A is a property of the problem. Ti you can set to all possible. It's also part of the input of the problem. It has nothing to do with your numerics. The only thing that has to do with your numerics is the h. So this is really a constant times h, which means that as h goes to 0, the error goes to 0. Proof of convergence. A typical problem here, I know this is a little routine, but let's do it anyway, would be something like this. 5, 2, 1, and 3a, where they ask you to solve the following equation. Y prime equals t e to the 3t minus 2y. And usually we do something simple like 0 to 1. And we start at, in this case, 0. And also they ask you to solve this with Euler. So they give you an h, which is 0.5. Okay? And this is actually so easy that you can almost do it. As I mentioned, you'll see on the old exams, we can choose numbers so you can do this by hand on the exam. These numbers are actually easy until the very last step. But Euler is simple. It says W0 is equal to the starting value, which is 0, right? W1 equals, well, this formula you definitely need to know by heart because it's fairly straightforward. The previous value plus h times the slope. So you keep on writing 0 plus h, 0.5 times the slope. And what is the slope? Well, the slope is given by the value at the previous step because of the equation. This is kind of this fundamental step that comes back in analysis and everything. At some point, you've got to use the equation that tells you that the slope of the function is given by this expression. So here you just plug that in, which of course gives 0 times e to the 0 times 0 minus 2 times 0. So actually, it ends up being 0 again. Seems like a bad approximation, but who knows? And one more step. And you got to keep track of what these means. Remember that if you change h, these things will be approximations at different times. It's a pretty obvious statement, but you noticed in your programming assignment that for those of you who grabbed number 401, you realize that when you divide h by 2, it was 801, etc., right? It just moved around. Because what W1 means depends on h. In fact, it exactly means y of h, which is approximated by W1, right? And y of 2h, which is the nth time in this case, is approximated by that. So it changes with h. Anyway, let's do this one too. It's 0 plus 0.5. Here you get the t there is 0.5 times e to the, yeah, now it's going to be something else. The time, there's a 3 there, and there's a time of 0.5. And then you get minus 2 times 0 again. Okay, and when you do this, you get some number. 1.1204. All right, seems a little iffy. I mean, I think intuitively you should feel that this is weird. We take one step, we get 0. We take one step, we get that. I'm not saying it's wrong. It seems like I wouldn't just trust these results as they are. It's not like they're varying smoothly. Not in any way a straight line between these, which is the approximation done in Euler, right? And if you have 0, 0, and then a value, right? I would intuitively say that this is probably inaccurate. But anyway, so in the next step, they ask you to, in 3a, they ask you to find a bound on this and look, this is a routine problem to confirm whether that bound is true or not. And so how do you do that? Well, you use the formula. But to do this practically, as I said, unfortunately, you need the true solution. So they give you the true solution. True solution. And they say it's y of t. Unfortunately, they should have chosen better numbers here. It's 1/5 t e to the t minus 1/25 e to the 3t plus 1/25 e to the minus 2t. So they gave you the true solution. Okay? And then they ask you to bound the error. Bound the error. So what do you have to find? You kind of know everything, right? You know A, that's 0, that's the starting point. Ti is going to be, as I said, all possible. But if you look at this error bound, what Ti are you going to plug in for the worst error? 1, yeah. So that's, if it's formulated like that, then of course you maximize the Ti. Because it's a positive, L is positive, right? So that e to the L times Ti is only growing with higher Ti. And L and M are the numbers that are properties of the problem, and you got to find those. So that's kind of what it's about. So first, M, which remember M is a bound on the second derivative. Well, as I said, there are short. This is a big flaw of the mechanism, but in this case you just differentiate. So you just this is boring. But it turns out, especially since there's a t there, you get product rules are coming out of this. So I'll just write down the answer, and then you can use Wolfram alpha or something. 2/25 e to the minus 2t. And then there's one more. 21/25. So actually, the numbers here are not that important, of course. I would hopefully choose better numbers for you on the exams if I had you do this. But anyway, eventually you get the y double prime. Now what? In a way, you might have to differentiate again, but we're not going to do it. We're gonna just do some hand waving here. But just the big picture here is that you got a y double prime, and you got to tell me what is the largest possible number for this between 0 and 1, right? And the way you do that is the good old math 1a, plug in the boundaries and find the extrema, which is another derivative, right? But usually we make some argument, and I think you can convince yourself here by the growing nature of this. You can bound that to be that. I'm just going to say that this y is increasing. And if you easily can see that, we often have 1 over 1 plus t type things. Then it's obviously decreasing. If there's an exponential type thing, it's obviously, you can easily figure out if it's increasing. I think most of the problems you've done are of that type. Okay? Especially on an exam, I don't really want to test your Math 1A skills. However, it has to be done right. And sometimes, if it's a function that looks like this, you can't just look at it and say what the maximum is. Right? But suppose you convince yourself that this one is increasing. That means that you can choose m to be the rightmost value, right? And that's equal to something. 53. So a huge number. And I think this confirms my suspicions that this is iffy. I mean, this is a huge number for the second derivative there, and we'll see what comes out of it. Anyway, more. Lipschitz. OK, so you got to find the Lipschitz constant. You might want to warm up by just saying, is it Lipschitz continuous? Is this expression here Lipschitz continuous? And I mean, the way we do it is by finding the Lipschitz constant. It's actually very nice. All these e's might scare you, but there are no y's here. It's actually a linear problem, right? Linear and y. It's linear first order. In fact, you can solve these things using techniques from Math 1B. That's probably how they did that. Now, anyway, it is certainly differentiable. And you can just use the theorem we said before. Namely, you look at the derivative and bound the derivative on the interval. All right? Question? You mean for finding the m? Yeah. You can do that. Let's see. So you differentiate the y prime. You get a bunch of product rules. A y prime pop out here. Then you're going to plug in this again, right? But you still don't know the true solution. Well, I mean, you're right. If you know the true solution, that might have simplified it a little bit, right? So what's your, but without the true solution, there's no way you can bound m, really. So you differentiate this, then you get some expression, and there's going to be a y prime here, right?
You already know y prime, right?
Yeah, and then you plug this in, which involves y. But we still don't know why. But you're right that in this case, it might have saved me a little work here, right? I didn't have to do that, maybe. So maybe you're right. But from a practical point of view, it's just very, I mean, if you don't know anything, how could you? But these are the type of tricks people actually do. They rewrite the equation in what's called an energy form. You can take the square root of it and do some tricks to actually get it out. So it's in towards that direction, the tricks that people do. Why did I put, is that a norm? No. Sorry. Anyway, yeah, so Lipschitz tells you that you just look at df dy. OK? And this is actually, in this case, really easy. It's really just 2, right? So this is your L. OK? Usually it's not that easy. L has to, again, be, it's a lot of maximizations here. I think in every part of this course, what have we maximized? Remember the fixed point iterations showing that they existed. It was just a big question of showing things were never greater than 1 and stuff like that. It's a lot of optimization of 1D functions. This one also has to be an upper bound on all possible L's that satisfy, or derivatives in this case. Anyway, now you're done. So now you can say the following. The error, by error I mean the left-hand side at the bottom, is bounded by hm over 2L times e to the L ti minus a minus 1. And you might think this minus 1 is, why do I even put it there when we have a huge exponential here? And that is true. If this is huge, of course, the 1 is not very important. But why is it important to have 1 here? I mean, it's correct. So that's one reason. But if I took away that 1 and say, I'm sure it won't matter, what would this formula tell me that the error is at time a? Then I would get something coming out of this, right? A 1 here times that, right? That doesn't make sense. I need to start that. So at least this formula tells me correctly that if you plug in time a, starting point, you get a 0 error. It's kind of nice. Anyway, plug in all this in. I'm not even going to do it. Yeah, I'm going to do it. I'm just write it like this. you had a time step, you had an m, 47, you had a 2, and you had a L, right? And then you get this exponential, and I'm just going to leave the ti there and the minus I. So this is the expression for the error. All right? And of course, eventually you often plug in the worst case, like I said, and you get an error that is less than or equal to 42.3654. Okay, that's, you might want to stop and think about that. We computed a value at ti that was 1.12, and the error bound tells us that, oh, I guarantee that the error is not more than 42. I told you it's kind of worthless, but if, yeah, that's what this formula does. You can, of course, look at the actual error. Maybe it's right that, actually, what I just said doesn't show that it's an unreasonable bound. If the true solution is 40-something, right? Then it's a great bound, right? So the only thing I argued here was that it's kind of, we're really far away from the true answer. But the bound might be great, but it's not. Because the actual error is, of course, what you computed minus the true solution. And we have the true solution. Again, you cannot compute actual errors unless you know the true solution. So in practice, this is kind of a problem. But this is something like 2.0987. So that's pretty depressing. Anyway, so what do you do if this is you trying to approximate the solution here? What's the next step? Well, there are many answers to that. If you want to keep things simple, here, and you have a computer code doing it already, lower h, right? That will make it better. I don't know how much smaller, but the error bound will tell you. Because this bound here, I mean, the error bound was bad, but at least you know it scales linearly with h, right? Divide h by 2, the error bound will go down by 2. Maybe the error, the actual, you know, divide it by 10, and you're still pretty far away. Divide it by 100 if you have it in the computer. But of course, the right answer is to switch method. Let's first look at the definition. I mentioned it already before. We're going to need a few pieces to analyze these methods. One of the most important ones is the local truncation error, which tells you you're taking one step, what is the error you make? And it can be written in various ways, but roughly it's what I said before, that you take the Taylor of your y ti plus 1, and then part of it becomes the method, in this case Euler's method, and the rest is the local truncation error. But there is a division by h as well. So the local truncation error here is going to be h half times y 2 primes. Anyway, this is just a definition, and we'll show how it pops up in the analysis. But that tells you the error you're making at each step. And it also tells you how to improve it. Why don't we keep one more term? So the higher order Taylor methods are based on that. So you do exactly the same thing. It's just that with Euler, we stopped here. In fact, we stopped here with Euler, straight line. And then we said this is the error term, the local truncation error, right? So higher order Taylor method just keeps on going and stops at n. And all of the n terms, n plus 1, go into the method. And the last one is used to bound the error. OK? The usual game, of course, what did Euler do with the y prime in Taylor? Euler said next y is equal to the previous plus h times the slope, right? The reason Euler works is that it says the slope is not a magic thing we don't know. It's the f, right? So of course, if there is a y 2 primes, you replace that by f 1 prime, etc. That is, of course, something you have to do. Anyway, this leads to the Taylor method of order n. It's summarized on the next page. You can actually write it as new value equals the old one plus h times something. And that something is, in the Euler case, really just f. But for the higher order ones, you keep on adding things. And I did mention that this is an issue practically, because how can you come up with those derivatives? And a short example of that would be the following. So what did I find here? So an example of Taylor's method on the equation y prime equals t plus sine y. So in order to devise, I mean, a typical problem here would say, what is Taylor's method of order 3 for this problem, right? And the difficulty is, I mean, saying what is Euler's method would be completely trivial, but maybe we could ask those questions anyway, but that's just writing it down, right? But Taylor's method has the difficulty that you need to identify the f primes. So let's do that. So what you got to do to write the Taylor method here is to say you have an f, and it's a function of ty, and it's given. Now the method tells you that you need y2 primes, which is f1 prime. And the confusion here is a lot about total derivatives and actually just a notation of what does a prime mean. Okay? But it's because this prime is consistent with the prime that we used for differentiation with y. Y is just a function of t. The f here is the issue, which is a two-dimensional function, right? I mean, it's a function of two variables, which is a little confusing. But this prime means the same. So it's a total derivative with respect to t. And the way to interpret it is, of course, that there's a t there. There's a function here, and we could talk about df dy. We've done that over there, which would be just the usual partial derivative with respect to y. But no, y here is a function of time as well, the true solution, right? And that is, when you take a total derivative, you've got to take that into account to really get how this function f changes with time. That's what the derivative means. The way you actually do it is the usual trick of the first one, the partial with respect to t, times the inner product dt, which is 1, so we don't even write it. But the other one tells you do a partial with respect to y, and now you need an inner derivative of y with respect to what you actually want, namely time. Okay? These two numbers are things you can, in principle, easily compute if you have an expression, right? What do I do with this? The equation. When you see a y prime and y is the true, then you plug in the equation. So that's the plan. So in this case, the f dt is 1. The f dy is cos of y. But then you have to multiply it by dy dt, which is f itself, namely t plus sine of y. So this is how messy it goes. And now we could finish if we want the Taylor method of order 2, but let's do one more step. So of course you just keep on going. I mean, it's identical, it's just that you apply it on this equation. But actually what pops out is still f. So you'll see what happens here. So the way to do the second derivative is that you target this expression here and do the same thing. So you write it as the partial of f prime with respect to t plus the partial of f prime with respect to y. But of course, f prime still depends on t and yt, just like before. So the thing popping out is not an f prime this time. It's still an f, right? Maybe that's the only. Otherwise, I'm doing exactly what I did before, but on this new expression. So now you have to differentiate this expression with respect to t. The 1 dies, but there's a t with a partial derivative cos y in front of it. Then you have to differentiate it with respect to y. And times f itself. So let me go over here. So when you differentiate with respect to y, you get, what do you get? Minus sine of y times t. And then you get plus, and here I did some sort of double angle thing. But anyway, you get to differentiate that expression. Okay? And then times this guy, which is just f itself, which is still just t plus sine of y. And you can probably leave it in this form, or you could simplify it a little bit. Doesn't really matter. But it gets messy, even for a simple equation. This is a really simple equation. But these derivatives get a little bit messy. Anyway, if you're asked what is Taylor's method, of course I'm not done, right? But you can essentially copy that theorem, but you have to do it. So now the method is wi plus h times f. And I'm going to use this short notation here. H squared half fi prime plus h cubed sixth times fi 2 primes. And if you really want to clarify that notation, when I say fi, that's just a notation for f at ti wi. When I say fi prime, that's just a notation for the same thing here. That's it, right? When you come this far, now it's like Euler. It's just messier, but you just plug these things in. The main drawback I mentioned with this method is this. It's pretty obvious, right? If this was RK4, I would be done a long time ago. So this is the motivation, at least how they present it in the book, which I think is great, for why we don't like this and we'd like to look into other methods. Anyway, it does give a lot of understanding, though. Is this a good method if you do all of that? Well, the truncation error can be shown just like Euler had the next term. So Euler basically had the term you cut out to be this, divided by h to be the truncation error. Now we have that term in our method, and one more. So actually the next term, which is an h4 divided by 8, is going to be an order h3 truncation error coming out of this. So I think we did this back a long time ago and showed MATLAB examples that showed just how, in fact, we should probably it was a different equation, but the equation we had before would be interesting to see with the same h, how much better it got with this method. And it's usually counterintuitively much better to go second order. Anyway, we have a theorem telling what I just said, namely that if you go to n extra terms here, you get a truncation error of order hn. So that's the Taylor method. Now that you know about implicit method, are these methods explicit or implicit? Remember, implicit method meant that you had to differentiate, you had to solve a system in order to get wi plus 1. Program assignment 4, in order to get I plus 1, it shows up here as well, right? Well, explicit methods don't. They just let you do things straightforward. The Runge-Kutta can look messy, the explicit Runge-Kuttas, but usually you can just do it. Here, of course, there are no issues. There are only wi's showing up here. So no matter how messy it is, you can in principle just evaluate it and plug it into here, right? While backward Euler, as simple as it is, it has a wi plus 1 showing up here. That's an implicit method. So these are all explicit. All right, so I'm not going to go through the derivation of all these Runge-Kuttas. They warmed you up by saying, look, we have functions of 2 variables. We better need Taylor in 2 variables. We actually never used anything more than the linear terms for that. So it wasn't the end of the world, but it looks messy. Especially these expressions. I'm not sure they even teach you this stuff in Math 53, but maybe they do. But the goal was, as I said, kind of pedagogical here. We don't really use this from now on, but they said that, why don't you try to approximate? So the second order Taylor method looked at f, and then it added this little term h half times f prime. And it's like, can we get that term without f prime? That was the whole goal. And what can you do? What are you allowed to do in your method? Well, it would be great. Of course, I'm going to evaluate f all the time, right? But to get information, the key here is to step away a little bit from t comma y. Or more particularly, all these are just evaluating at ti and wi, right? And therefore, it needs Taylor, it needs higher derivatives at the same point. Why don't we just step away a little bit from this point? Taylor will, we know, bring in a lot of partial derivatives here that are mixing things up. I'm not saying it's easy, but it should give us some information that we magically can match. And that's what they do here by saying, let's see if you can step alpha 1 to the right and beta 1 up, such that you get approximately this term coming out. And by just plugging into Taylor and doing, of course, here exactly the same expression as we did here, you're going to have to expand this total derivative with respect to time. You can actually match terms, and the end result is a method. This is what you get at the end, where you get all these terms coming out of the second, the two-dimensional Taylor there. And you can match coefficients to get some sort of solution out of it. So it does work. It's not, these methods are not identical. Let's see if we summarize the method. Here's the summary of the method. It's called the midpoint method. Turns out that if you go h half to the right and h half times f, the old f. So a way to see, I would read that right-hand side to say, this is half an Euler step. wi plus h half f is half an Euler step. You go there, and you evaluate a new slope that you take a full step with. That's, in words, what this method is doing. And it came out of just putting these together, the simple assumption that we want to do Taylor without. This is not identical to Taylor, but it matches the same number, the relevant number of terms. So that's an excellent method. So much better than what we did here, because there is only an f, right? There is no f prime. So much easier to use. It's a one-step method. Is it still explicit? You just look at the expression and look for wi plus 1s, basically. If you can do it without thinking too much, without writing a Newton solver, then it is explicit. This one, of course, we used over and over. We never verified the fourth order accuracy, but at least you did a bunch of other things. You looked at writing it in wrapped form, in this nested form instead of the K1s, K2s. We went the other way as well within some homework exercises. I don't like this form. It usually gets very confusing. Better is to have a K1 equals F, and then make this here a K2. That's how we like to write the Runge-Kuttas. But it's kind of the same thing, and we had some exercises showing that. For RK4, you definitely want to write it in this K form, especially when you implement it in a computer, or you will certainly mess it up. So we did talk a lot about my RK4 function. You've used it a lot. You should be very comfortable with it. It's really just almost like Euler, but just doing one more step of so Euler would really just compute this K1, which is h times f, and it would add it to wi to get wi plus 1. The only difference here is that you do a bunch of other k's that are, in a weird way, connecting all these k's in a nested way, and adding them up in, again, a non-intuitive way. But it can be analyzed. But from an implementation point of view, RK4 is really just doing the same type of operations as Euler, namely computing slopes at various points and adding them up. Extremely good method, still, of course, explicit, as we said. You've seen the properties of it. What was the point about this chapter? This was the idea that we need to change step size. So there are two main ideas here, basically. One is that how can we adaptively change step size as we go? And that was this Runge-Kutta-Fehlberg algorithm that you worked with. The other step is how can we estimate the error? I mean, if you want to automatically change the step size, you better know if you are allowed to do it or not, and that's based on an error estimation. So someone needs to tell you if the step you took is okay. Okay? And we'll see what the algorithm is, but the method we're going to use here is actually very simple, much easier than what we do later for multistep. Namely, we're going to look at two methods, one twiddle and one that you want. Okay? And the twiddle method is better than the one that you want, which can be discussed, but that's what we're going to do. That means to the first order, by simple calculation here, by subtracting these guys, you can roughly say that if you subtract the more accurate one from the less accurate one, you get an estimation of the error in that step. Okay? And you should, of course, ask yourself, why not keep the good one? Well, that's because then the error estimation is not a good error estimation. But people actually do that. They keep the good one anyway. But that can be discussed. So the truncation error is, of course, then just the difference, and there is divided by h in the definition of truncation error. That's a very easy way to estimate. If you wanted to, remember the first problem I did? I said I got a 0 twice. I said this looks weird to me. The way I would monitor it is to take a step, the same step with the midpoint method, which is second order accurate, and that value would be an estimate of that error. So that's the goal here. And then you have some more calculations here, which are really just bookkeeping, but it has to be done. So you are telling me you want a certain error, epsilon, okay? And you want to find a new step size, a multiple of the old step size h, so QH, such that the error is now bounded by epsilon. I mentioned numbers last time. You want epsilon 10 to the minus 3. You take a step, and the estimator tells you, oh, you got an error of 10 to the minus 2. What do you do? Well, you better throw away the step, and you better decrease h. How much should you decrease h? Well, it can be done, but let's just think of it. If it's Euler, we talked about that before. Suppose you have an error. Suppose this is your error estimator, and you want it to be 4.2. Suppose this is 10 times larger than you want it. You divide h by 10. That's because it's a linear method. Right? What if there's a square there? Then you only have to divide h by square root of 10, etc. Right? And doing the math for any method, you of course get these powers of 1 to the 1 over n, which is the order of the method. And so you have here you have the estimate of your error divided by h. That's the truncation error. And the epsilon is what you want it to be, and you take an nth root of this to get the reduction of time step. So that's fairly straightforward. I think when it comes to the method, I emphasize in particular that if q is less than 1, it tells that you need to shrink the time step. Then you have to reject the step, because you just took a step that was too inaccurate. If q is greater than 1, it actually wants you to increase the step size, which you can do. But of course, you keep what you just did. It's just too accurate, which is fine. Okay? And all this was shown in this RKF function, which I guess, I mean, it looks messy for all of those numbers, but apart from, and there were some hacks. I told them, you remember there was an h max and h min. There were some issues. But this fundamental strategy is really simple in a way. You just take two steps, or the same step with two different methods, And from that difference, you can estimate these steps. This is extremely practical. The RKF function that you use is not too different from the OD45 that is running in every online system or any type of hardware solving ODs. These type of methods are used. All right, this is going fast. Okay, this is the next big chunk, multi-step methods. I'll let you catch your breath. So why do we even teach these things? I think I couldn't hide my my opinion about Runge-Kutta versus multi-step. I think there are a few reasons for ever using a multi-step method. Having said that, people do it all over the place, and they have arguments that could be discussed. So it's being taught. It's really just a different class of method. And the main idea is this. In Euler, you said wi plus 1 equals 1 times wi plus something times f, right? And why not just allow you to use older values of w? Okay? This will allow you to interpolate back and extrapolate and do all type of things. But just, you're standing here, and Euler and Runge-Kutta, they all say you're only allowed to stand here and go forward. And there's justification for that, namely that the OD is uniquely given by one value. So the whole future is told by just knowing one value. And now I'm saying I need to know the history as well. It's a little iffy. But having said that, it can actually be used to gain quite a bit of accuracy. The definition is what it is. You're allowed to do any linear combination of old w's, and the further back you go, the higher order of the multi-step method it gets. A special case of the multi-step method is to say that you only have wi, then it's a one-step method. I don't know if that, can be discussed whether that is a multi-step, whether one is multi or not. But 2 is definitely multi. So if you go back to wi minus 1, you have a multi-step method. Of course, if you're using wi plus 1 in this form, why don't we allow for a linear term multiplying f evaluated at that point as well? And finally, to allow for implicit methods, why don't we throw in a wi plus 1 evaluated f here? Okay? Why didn't I put a wi plus 1 without f in the right-hand side? It would just move it to the left-hand side. So it's kind of there. In fact, all these numbers, you see there's a 1 multiplying here. You can multiply that by 10 if you want to. So this is a good definition. But it's all linear. I don't allow you to multiply w's and stuff like that. Well, in f you can do it, but the method itself is not doing that. All right, what did I say about this? Pain to implement. Not too big pain, but pain to start up. Because how could you possibly take one step if you don't even know where to? And you saw this in your homework problems. But basically, if you want to go from here to there, it would ask you for wi minus 1, right? So if you're standing at 0, it will ask you for w minus 1, which you don't have. You just don't know. So somehow, you got to take this step. Then you can use 2 old values to produce a new one. That's a big drawback. Here are some methods that we played with. Ernst Bashforth will derive some of them, but these are methods we just use to get to know it. The main way we derive these multi-step methods, yeah.
Are you going to start to memorize the formulas?
These coefficients are kind of stupid. I'm just, as I told many people, if I tell you to derive this, well, that one is messy. But if I tell you to derive, as you remember from the midterm, I kind of give you error bounds. I don't want you to memorize too much. Having said that, if I ask you to derive something, let's say I ask you to derive the local truncation error of Euler's method. We talked about it. It was h half f, the second derivative of y. If someone remembered that, they would benefit from knowing it, right? But no, I don't really believe in memorization. You can tell from my old exams and the midterm and from, so I mean, these numbers are insane, of course. I wouldn't memorize those, no. Might benefit you slightly from remembering the simplest. It's not even here in the slides. OK, so there's nothing to remember. No, don't do that. Anyway, how do we derive these methods? It's a nice intuitive way to derive them, that you actually look at fundamental theorem of calculus, which tells you can integrate f from ti to ti plus 1. That's exactly how you go from y ti to y ti plus 1. You could think of that. If you, in principle, could integrate f exactly from ti to ti plus 1, of course, that means that you just gave the step from yi to yi plus 1. The only issue? Well, you know f, but you don't know y, and f depends on y, right? So that doesn't work. So the idea behind these methods is to predict these y's or extrapolate by a polynomial p through the old points. So as I said, you take the old points, for example, these 2, And these are actually y values. When we draw it, it's usually y. But of course, I'm going to look at the slope. And that might be down here. So these are y's, these are f's. And you take two of these slopes, and you extrapolate with a line. This chunk here, if you integrate it, that gives you the jump from there to there. That's what the fundamental theorem of calculus says. Not exactly, but if you extrapolate it, you get an approximation. So that's what these methods do. Fairly straightforward to do. You just find that polynomial. We could by hand derive this method, doing exactly what I drew here, and that is the Adams-Bashforth 2 method. Okay? Remember, if I approximate it by a constant, it's Euler. If I approximate the slope by a constant. That's the same thing as approximating the function by a straight line. Here I approximate the slope by a straight line, extrapolate it from these points, and you get something else. One more order of accuracy. And here are a bunch of steps that were done. I think understanding is more important. So again, memorization here doesn't seem very fruitful. But having said that, if you did remember this form and I asked you to derive Adams-Bashforth 2, you would get to the result in 1 minute instead of what we did on the blackboard, which was 5 or 10 minutes. And some other methods. All right, and the local truncation area is defined. You might want to remember this as a new definition. To me, it's just the same thing as before. What are you cutting off from the true Taylor? But if you don't want to see it that way, just remember this definition. Because a typical routine problem, and I have one here for you guys, is what is the truncation error? So, so let me just look at that. Yeah, let's do that now. So let's look at a typical multi-step method and its truncation error. It's, of course, a good idea when you get questions like this to quickly identify what it's a question about. So when I show you something like this, wi plus 1 equals 4 of wi minus 3 of wi minus 1, you immediately say this is a multi-step method, and you just retrain your brain to realize that. You know we always do these shorthands, and you should immediately identify this as being this f term evaluated at ti minus 1, right? More identification, if not that it matters so much for this problem, but you look at this and you immediately say that it's an explicit method. If I put an fi plus 1 here, it becomes implicit, right? And that's in the theorems, of course, but I don't, so this is an explicit method. It's a multi-step method, that's about it, right? And then you're asked to find tau. So the question would be, find tau and determine if the method is, and actually, you know, I might even give a hint to say just convergent here. And this is, so this is really a routine problem in this. You'll see a lot of them in the old exams. And it's asking you, finding tau is, of course, more routine. That's immediately. That's not even thinking twice, right? You go at the definition and you start doing your Taylor. And we'll do it. But what do you need to do to show this? What chapter is this? What section? Yes. So how do you show that the error goes to 0 as h goes to 0? Is it enough to find a small 8, tau? It's not enough. So this is chapter 510 material, which we will come to soon. But I'm going to start with the first part. Okay? But it's a typical routine problem. Remember, to show convergence of a multi-step method, you need a stability and a small tau. So that's what these problems try to test. Anyway, so let's start by tau. You simply just copy the, you just plug it in, basically. So let's see. All right. So tau I plus 1 h. It gets a little messy, but this is actually not that bad. Okay? So I'm going to write it like this. I like to see it as plugging in the true solution in the equation and dividing by h and moving everything to one side. That's my way of remembering it. If you want to use this formula here, you can try to match what I just said. But it's going to be yi plus 1. I'm going to subtract the 4yi. I'm going to add the 3yi minus 1. And I'm going to add the 2h fi minus 1. And I'm going to divide by h. And you can confirm that these first parts here is, of course, this big chunk here, right? And then they actually divided away these h's for us in this expression. But my little memorization didn't do that. But it's the same thing. All right, what do we do now? One word, Taylor. Everything, you can actually be smart sometimes and choose a good point. But if that's too confusing, why don't we just, I think in everything we've done, we tailor around ti. Okay? So this guy is fine. That's the only one that is fine. In fact, in this problem, it would probably be smarter to tailor around I minus 1. Am I doing that? No, I'm not. I'm not being smart. That's OK. Because that shows more that what we have to do. But anyway, you see the point. You can choose your Taylor point, but you got to make sure terms cancel out. It's the same game all over. So you take your yi plus 1, and you can probably almost immediately write it as a yi plus hyi prime. And everybody wonders how far should we go. And you'll get some experience after a while. But if you go too far, it's not the end of the world, except that you get tired and confused from all the things. If you go too little, you will actually also reach a conclusion that, wow, it might be better than I think it is, or I need more terms. So I think it's kind of adaptive in that sense. But having said that, I don't quite know how far to go. Depends on how many terms you're going to cancel out. Before the yi we leave, and then we have a yi minus 1. That's really the same thing as here. It's just that now h became minus h. This is really y of ti minus h. So I'm doing a step to minus h in the negative direction of h with Taylor. So this would be plus 3, and that's the same thing as there, yi. And then you alternate the signs here, yi prime. You get a plus h squared half yi 2 primes. And then there's an, I'm going to squeeze in the order of h3 there. Sorry about that. Just because I really want to put this line divided by h. Okay? But what I wrote here is exactly this. But the odd terms get a minus sign, right? I can't see it in this guy because it's just a plus order h3. We don't care about signs or constants, right? So the only actual minus signs I got was this one. Anyway, one more. The h is cancelled out, as we said. So now I have an fi minus 1. That's also Taylor. And it's really identical. It's just one level of primes and y. Yeah? No, it's because I have old stuff. Sorry about that. Thanks. Yeah, things are lurking behind and messing up my expressions. But no squares. Anyway, so what do we do with fi minus 1? Do you all see that it's really exactly what we did here, but one extra prime on everything? It's just f is y prime as a function, it's a function of time if you wish, or a function of t and y explicitly, right? So you just do the same thing, and then you get minus h yi 2 primes. And I guess I figured out here, oops. I guess I figured out that I can stop already now. How did I figure that out? Because if I stop at h3 here, this is divided by h. Then at least to be consistent, I should stop at h2 here. Anyway, then you collect terms, and you realize that you have, OK, one more line here. So let's stay up there and collect terms multiplying yi. We have 1, we have minus 4, we have plus 3 yi's. And then you look at the yi primes, and it's a good idea to take out the h and realize that you have one of these. Of course, this guy is done, because there was no Taylor, right? But here we get a minus 3, and that's multiplying yi prime. And one more. We have a bunch of h squares, and they will always show up as h square halves. And how many of those do we have? We have 1 plus 3. And that's multiplying yi. All right, just collect terms. And these are going to all zero out. Not all, but as much as possible. The f is coming. I'm not there yet. Order h3. Let's stop this now and divide by h. And then we do the f. I'm not going to do anything to f right now. I just copied it. And now I think we can finish it all in one line here. because you're getting 0 yi's. Now you got to think a little bit, because when you divide by h here, it combines with this guy, right? So I would say, to be explicit about it, you're getting the 1 minus 3 that you had, but then you're getting plus 2 of yi 2 primes. Sorry, 1 prime. Right? One more. We're getting h squares here. And I guess I don't have a square there, so now I regret that I did this fancy trick here. So let's just do h square. Then we have 2 plus 4. So I guess this is a 4, right? Well, let me write it like this. But how many h squares do I have here? Or I divide, did I say h square? Of course, I divide by h. Sorry. So you divide this h squared by half. You're getting a half times 1 plus 3. Here, you're getting minus 2h multiplying. So I'm getting minus 2 here. And this all multiplies yi 2 prime. And now I'm done. Well, we can discuss whether I went far enough. But clearly, this is all equal to order h squared. And that's the final answer. All right, so that's the routine part of it. Did I go far enough? What would the question? Did I really find the leading order of the local truncation error? I did not go far enough. Because maybe all of these O3s that I just skipped would cancel out. It's a lot more work, though. So even if they do, it was good to start here and just go step by step. If the question was said, show that the truncation error is at least order H2, then you would be fine. Or if you just answer this at least. But if you really want it, I just don't know. It might be order H3. All right? And just to be able to finish this and the question of convergence, we found tau. To determine if the method is convergent, let me quickly jump to 510. We come back here later. The idea there was, in 510, first of all, we defined a bunch of terms. In particular, what does it mean for convergence? And you all know what it means. The question is, how do we show it? Okay? So local truncation error, tau, is consistent if it goes to 0 when h goes to 0. That's the reason we write order h squared, etc. It goes to 0, right? So if I ask you, is this equation consistent, you can answer that already now. The answer is yes. If the truncation error was 2 plus order h, the answer would be no. Consistent means truncation error goes to 0 as h goes to 0. But convergence is more difficult. So here we had a big slide telling you that one-step methods have no more issues than tau. If you have a consistent method, it's also convergent. Pretty fundamental. It even went further and said, here's a Euler, the same expression you had for Euler works now well if you just replace tau by your truncation error and L by an updated Lipschitz constant. But one-step methods are amazing in that point, in that sense. While these ones, hey, finishing up, just about the multi-step method. They are not that amazing. You need to look at the root condition, because I remember I showed a simple equation that looked great, and it just blew up when we tried it. That's the issue that can happen here. And if you look, what you do is just that you define this root condition that you take the coefficients a multiplying w, so you have the 1 here, the 4, and the minus 3, right? And you look at the corresponding characteristic polynomial. And in this case, it becomes root condition. So it would say that this characteristic polynomial is lambda squared minus 4 lambda plus 3. Okay? If this has any root greater than 1, you're in trouble. And there's also the little tricky thing that if it's on 1, it cannot be duplicated. Okay? But this you can factor into lambda minus 1, and there's a lambda minus 3. And you want to find the roots here. So lambdas here are 1 and 3. What is the conclusion? It did not satisfy the root condition, right? Then it's not stable, and therefore no convergence. So in a way, from a practical point of view, all this work we did for the tau is completely meaningless, because this method just doesn't work. In fact, if I really want to trick you, maybe you should have done that first. if I just asked, actually, here I asked find tau, right? Suppose I just ask, show if that this is convergent. Then you might want to be smart and first do that. Because it could be that it's 10 minutes of work to do the tau, and it's meaningless because it's not convergent anyway, right? So, but anyway, here it was asked for tau as well. Anyway, give me feedback what you want to talk more. We did most of 5 now. I can keep on going with 6 and more 5 on Thursday or anything. But now at least they want us to do these course evaluations. You have to give them to Dave when we're done. Let's see. I'm going to take out of them. When did you do one? That's good. How do we send